On the. It's working? Okay.
Yes.
Are we live? Types from University of Chicago and Mana Temporary. He's a resident artist. He's a physicist. Right?
Yes.
That's right. So he got his bachelor's in physics from the University of Sorbonne.
Yes.
Yes. And then he went to Harvard. to do
PhD at Sorbonne, sorry.
Yes, and
Yeah.
PhD at Sorbonne too. Then he got a postdoctoral appointment at Harvard and then MIT. And there he got this commit grant, right, for interdisciplinary research involving physics. And then he moved to Chicago.
Exactly.
And then in Chicago, he has like 2 appointments, right? One in the James Clark Institute of University of Chicago, and as a researcher that tries to apply his physics related research into robotics and art.
Yeah.
Kind of interdisciplinary research. Yes. So his primary research is basically exploring the relationship with the artistic creative workflow by the development of technologies that allow integration of audiovisual immersive narratives and real-time projections of live experiments that is done through complex physics, and which we're going to learn today in his latest work that encapsulates in the shapes of emergence, experimental physics, and new media art. So let's give him a warm welcome. Dr. Saintyves.
Thank you, Izaru, for the introduction. So today I'm going to talk about this project, Shapes of Emergence, that I started a year ago. And so it's an art project, but it's based on science. So this talk is going to be in between an art and science talk. And if it's confusing, feel free to interrupt me and ask me some questions. So I am a physicist and an artist. And as much as a physicist and as an artist, I am interested in how self-organization processes lead to the emergence of shapes in nature, spontaneous emergence of shapes in nature. So by shapes and patterns, I mean objects with a typical size, a typical length scale. And by emergence, I mean objects that can, also I mean like shapes, like it's an object with a certain form. And by self-emergence, I mean objects that can arise spontaneously in nature without the intervention of a human. So it arises completely from the physical condition. Okay, so so for example, in this image, you see that without even telling you what it is, you see that there is this wavy form, and that there is a typical land scale that corresponds to the space that you see between those peaks. So we are all very familiar with shapes made by a human. So human can engineer very complex shapes. For example, this car, or this desk, or this painting, and all these examples are basically objects that are designed in order to achieve a goal. For example, moving, working, or painting. So here it's like for the artistic expression of some artists. And then in this painting, we can debate a lot about the content of this art. But at the end of the day, on a pure technical aspect, this is nothing else than material, the paint, that is applied on a canvas in the most accurate way, so that the artist can represent what he has in mind. So you might think that shapes and patterns that emerge spontaneously from natural conditions might be coincidental and uncommon, but they're actually very ubiquitous around us. And the first example that I can give you is just if we get closer to this painting at a scale that wouldn't make any sense for an art amateur, but that make a lot of sense for a scientist. You can see, if you zoom in, that you have all these crack patterns. You probably have seen that also in other oil paintings. These cracks arises spontaneously from the physical condition. So, and there is many other examples. Actually, you can see this kind of pattern in a completely different context. For example, here in a dry lake, it's exactly the same physical process, or also on the surface of a ceramic. In all these examples, the reason why you see cracks is because the material is made of two components. It's made of a solvent, a liquid that can evaporate, and then tiny particles that cannot evaporate. And all these materials sit on a layer. In the case of the dry lake, it's a layer of soil. In the case of the jar, of the ceramic, it's a layer of clay. In the case of the painting, it was the canvas. And so basically, when you evaporate the water from this layer of material, because it's constrained by the layer that is below, the material doesn't want to shrink. If you evaporate water, the material wants to shrink, but it cannot because of this layer underneath. So at the end, you build up stress, and this leads to the formation of crack. So it's a very simple mechanism. So another example that I like to show is sand ripples. So here the reason why you see these patterns is because the sand grains can be transported by the wind. And the way these sand grains are transported by the wind will drive the length scale that you see. So the more the grain can be transported, the more space you're going to see between these ripples. So either because your grain is lighter, or because the wind force is stronger. So another example that is also very nice is if you just go for a walk during the winter, you see snow around, and if you look closer on one of these snowflakes, if you are lucky, you might see a structure like this. And the reason why the water organized in such a nice way is because the microscopic structure of water molecules is special. Water molecules organize themselves in a special way. So, and at the end, so this is something that is fun with a snowflake. Every new formation of a snowflake gives rise to a different shape, as you can see on this video. So here, this is a video that is an experiment that. Oh, sorry, what's going on? No, this is. Oh, sorry. So here you see a video of a snowflake that is growing under a microscope. So this is a shape that you can have. And after that, you're going to see another shape. If you redo exactly the same experiment in the same condition. And we don't really know why every time it's a different shape, but it's a pretty nice thing to look at. So far I've showed you systems in which there is no life, non-living systems, but you can actually also see emergence of very fascinating shapes in the context of living systems. For example, in the case of bird flocking. So here, very local rules and very simple parameter like reaction time lead to this kind of behavior. And you can see that here there is a falcon actually that is trying to eat one of these birds, and you see that the birds are able to very efficiently react and move around. Okay, so now that I show you all these examples, I just want to tell you a bit more about my path and my research work as a physicist. So, and how I ended up developing an interest in through this topic in art and science. So way before being interested in this topic, the physics of shapes and pattern, and even before studying physics, I started to play music, and so I had a very I already had some incline. I was pretty inclined to do artistic activities. I was also very into physics, so I decided to go in for my undergrad in physics. And so this and at the same time that I was doing my physics, taking my physics classes, I also took cinema classes, and this was a very important thing for my path. This is because of the cinema classes that I took that eventually later, when I discovered this subfield of physics on patterns and shapes emergence, I decided eventually to really explore this because it's a very visual physics kind of things. So, and at this point, I was really driven by exploring this area. I was driven as much by aesthetic interest than scientific curiosity. And I really wanted to have both outcomes from my work, artistic and scientific, which is not the most, the easiest path in terms of career. And my first opportunity was to study a very interesting pattern formation problem in physics with a very inspiring advisor. And I started to explore the pure science aspect first. Then I had other very interesting opportunities at Harvard and then at MIT to study the physics of shapes. And this is in this last place at MIT, like Isuru said in his introduction, that I started to work on this art project with this grant from the Council of the Art at MIT. So, and as a physicist, what I am interested in is to identify, to isolate some of the physical effects that you've seen in this example and many other situations, to isolate those physical effects, bring them in the lab, build minimal experiments in which I can study how these minimal effects can lead to self-emerging shapes. So to illustrate that, I can show you an example of an experiment that I did inspired by these flocking images. So I told you that here one of the very important effects is the reaction time of the birds to see this behavior. So I just wanted to find the most simple system in which I could study the effect of response time. And so what I did is that I bought a bunch of these cat toys called whistle balls. You can buy them on Amazon, they're pretty cheap. So if you remove the whistle, because the whistle is not very convenient to do research, if you remove the whistle and you open this ball, what you see is that. So it's basically an eccentric motor, and this can turn around. If you close that ball at the end and you just turn on the ball and just let it go on the floor, at the end you see an erratic motion. Now this is in an arena, so this is the trajectory of this ball. And you see an erratic motion, and eventually after some time the ball can have like a more coherent motion, a little bit like a bird who knows where he's going. So, I put a bunch of these balls together in an arena, and and as you can see here, it's a bit loud. As you can see here, as you will be able to see here, after some time, so I'm cutting the video somewhere because it's a pretty long process. At some point, the balls are able to cooperate together and eventually create collective motion. So I don't really have time to talk more about this research, but it's just a way to illustrate like this approach that I have. Another example is my PhD work. So here, what you see is a top view of an experiment that consists in an hydrogel that is in between two glass plates. An hydrogel is typically like the jello that you can have in your kitchen, can make in your kitchen. I'm using polyacrylamide gel. This is another type of gel that you should not eat, but it looks like this, basically. And if I create a cavity, an initial cavity in this system, and I pressurize this cavity, then you observe the emergence of this kind of patterns. And I showed during my PhD that these patterns arises because of the very large deformations that this material can undergo. They are very squishy, elastic material. So another example of experiments that I did is a drying experiment that I did when I was at MIT. So this is the same material, an hydrogel. An hydrogel is made of water. So here what I'm doing is that I'm evaporating the water in the same kind of system. So I have like two glass plates. and the water, so the gel is in between, and I evaporate the water from an edge, and you see the emergence of this kind of patterns. Here I'm showing you a movie. So the experiment is very long, so it's a time lapse actually, so it's way faster than the actual time. And you see those nice network, the emergence of these nice networks. All right, so after seeing all these, I mean, when you see all these patterns I showed you, either from my work or from these other examples, I think that we can naturally think, as many observers did in the history, that somewhat nature is making art, or at least because art is an intention, and I'm showing like stuff that I'm showing like a pure natural phenomenon. At least this is very interesting, and this can trigger in an observer some inspiration and curiosity, either if the observer are scientists or artists. And there is a quote that I really like from Jackson Pollock that illustrates very well this relationship between art, science, and nature. I don't paint nature, I am nature, as if the artist somewhat want to substitute his creative, controlled creative process for making an art piece with a form of nature. And it's actually fun. Some physicists took his word very seriously, and they look at his paintings. Here it's Alchemy from 1947. They look at his paintings, and they found by doing a fractal analysis, they looked at this painting as if it would be like a natural object, and they found by doing a fractal analysis, some scale invariance properties. So, which means that if you zoom in this picture, you will always see the same kind of randomness. So, just to give you tell you a few words about that. It's exactly the same thing that you would see in this kind of in this pattern that is called a Sierpinski triangle. So here, if you zoom in, you always see the same structure. So this is the same idea. So in the other case, it's more it's the same randomness that you would see if you zoom in. And this is something that you see in nature, like fractal are present in nature. For example, in the Romanesco cabbage, but there is many other examples. So at the end. What I really like with this example is that somewhat it supports this sort of willingness that Pollock has to substitute his process to a form of nature. I think it illustrates pretty well this duality between the artist and his conception of nature. So I don't paint nature, I am nature. Of course, this is a provocative quote, but I think it raises a very interesting question on the relationship between nature, creativity, and the artist workflow that I'm very interested to explore in my work. So, just to tell you more about my personal experience as a musician, when I write music, I'm always more fulfilled if I have accident on the way in the writing process. And at the end, I have almost the feeling that the result at the end is miraculous. And this is really like how I feel good about my work. A little bit as if I would discover the song that I'm supposed to write. Discover like a scientist somewhat. And I think that this is really partly where my scientist and artist sensibility come together. And so by accident, I'm in a force from outside that pushed me to react instead of iterate. So, and in Shapes of Emergence, in my artwork, I am interested. I want to explore the possibility of reacting to ongoing natural phenomenon to develop an artistic intention. So, and the idea is to create self-emergent to create the physical conditions that allow the self-emergence of shapes and to curate events, but constrained by a time frame that is imposed by nature's laws, instead of an iterative building process in which there is no temporality in the process of making the art piece. So, in a very concrete world, I build experiments that are very inspired from my experimental physicist work. I film shapes that emerge from these experiments. I film light and then I project in a room, and the idea is to create some immersive narratives. Yeah. So now I'm gonna show you an example of. I'm gonna show you a video, a 4-minute video, that I did. So it's a performance that I did in the lab, and what you're gonna see is droplets that are vibrating on the surface. All right, so now I'm going to tell you a little bit what is behind the hood and how I can make this happen, or I can make just with the droplets that are vibrating, or I can make the visual look like this. So first of all, I'm going to tell you a few words about the physics behind that. So the system consists in a speaker that we can drive with a function generator. So we just impose a sinusoidal oscillation. We can control the frequency of this oscillation and its amplitude. And so at the end, we control the vibration of the speaker, the frequency, and the amplitude of the oscillation. The droplet is on a plate that is on the speaker, and this plate is coated with a repellent material, such that at the end, the droplet can have this shape. And it's exactly the same kind of coating that you have on a lotus leaf, to give you an idea. So people have studied in the lab the behavior of such droplets that are vibrated on a speaker. So so first of all, why the droplet has this kind of shape when it just sits on the plate, and while it's oscillating when we excitate this droplet. So there is two forces that are at play here. The first one is surface tension. Surface tension basically corresponds to the fact that molecules of water want to be surrounded by other molecules of water. So the system is trying to minimize its interaction with surrounding environment. And so the most efficient way to minimize this surface is to do a sphere. So surface tension wants this droplet to be a sphere. And if you deform this droplet, basically the droplet is going to want to go back to its initial shape, a little bit like a spring at the end. So then there is another effect. There is a gravity. Gravity wants to spread the droplet. And at the end, the equilibrium between these two effects give rise to this kind of shape when the droplets sit on the plate. Okay, so now when I oscillate this plate, what I'm doing is that somewhat making this droplet a little bit lighter or heavier. Like if I would modulate the gravity somewhat. It's a little bit like when you are in an elevator and you are going downward, you have the feeling of being lighter. When you are going upward, you have the feeling of being heavier. And so at the end, when I'm oscillating this, I'm changing the shape like this, as if I would modulate the gravity, which would make eventually the droplet less squish, more spherical. Okay, so people have studied this droplet vibrating on a plate in the lab, and what they found is that in some regime, for certain range of frequencies and amplitude of the oscillation, you can see the self-emergence of this kind of shapes. And what is very interesting is that in this regime, there is an oscillation. Like what you see here is like this is a top view of the droplet. You have an oscillation that arises in the horizontal direction. Okay, the excitation is vertical, and you have in this regime horizontal oscillation that manifests itself by this the self-emergence of these shapes. So people have looked at the horizontal oscillation of these droplets as a function of the frequency of excitation of the speaker. And they found that basically the frequency of oscillation of the droplets is twice lower than the frequency of the excitation. Okay, so now I'm just going to give you a little intuition of this effect by doing an analogy with a simple pendulum. So when you take this pendulum, just make it move a little bit like this. What fixes the frequency of this pendulum is the length of the wire and then the gravity. Okay, so there is two parameters. Those two parameters are independent, and there is two ways of excitating this pendulum. You can drive it directly like this, but there is a much clever way to excitate this that we call parametric excitation. So, parametric excitation consists in oscillating one of these parameters that are at play in the mechanisms that drive that fix the frequency of this system. So here, for example, I'm gonna excitate the gravity by moving my hand up and down. So, and what you can see is that by doing this, I can I can excitate my oscillator, and in this case, there is even another mechanism that is called parametric resonance that makes the amplitude increasing. And so here, this is the same idea with these droplets in this regime where you see this oscillation in the horizontal direction. So now let me walk you a little bit through the cycle of movement of these droplets when it's doing like this kind of shapes. So here it's a mode 4 four lobes. Sorry, oh, it's not working anymore. It is on. Okay. So let's start with, we start with plates on the upper position. So in the upper position, you see this star shape. Then when it's going down, which corresponds to this phase here in the pendulum, when it's going down, you see a spherical shape. And when you go back upward, you see the star shape, but now it has turned of 90 degrees because actually this surface is oscillating like this. So here so basically the parts that are convex become concave in the next cycle. So here you see that basically in order to do a full cycle of the droplets, which has this shape and this shape as well, you have to do two oscillations here. So it's really like the same thing than in the simple pendulum. Okay, so now if we just look at this plate vibrating with a simple camera, like an iPhone camera, this is basically what you see. So not very interesting at this point. So there is definitely some other aspects that are very important, and this brings me to the next part, which is the setup that I built in order to see these visuals. So this is a picture of the setup that I use in this performance that you've seen in the video. So I'm not going to describe you the different parts in this picture because it's not very easy to understand. I made some sketches that are a bit more pedagogical. So I have a speaker, an amplifier. In order to excitate this speaker, I use a synthesizer, which is nothing else than a fancy function generator. What is very nice with synthesizer is that you can change the frequency just by hitting the keyboard. You can jump from one frequency to another one that is very different pretty easily, while with a normal function generator you have to play with just one knob. And there is also a bunch of functions. I'm not going to get into that, but there is a bunch of functions that make it very playable to control the visuals that you are seeing. Okay, so then there is a camera. That camera is a special camera. It's an industrial camera that we use in physics experiments, but it's also used in factories, in a production chain to do quality control and this kind of thing. And the nice thing about this camera is that they are fully programmable. You can write a C code to completely control all the parameters, which you wouldn't be able to do with a consumer kind of camera. So this camera is plugged to a computer that receives the video stream, and then this computer sends this video stream to a video projector, and I project in the room. And then there is a light. The light the light control is made with a microcontroller and a code I write typically in Arduino or C, and all the parameters of the lights are controlled via OSC, the OSC protocol. So you can build your own layout, control layout, that you can have in any tablet or your phone. So it's pretty convenient, and it's also through Wi-Fi, which is very nice because it means no need of wires. And this is very flexible, so you can really change the layout depending on the experiments that you are doing and the kind of parameters that you might want to use specifically. Okay, so, but now if I just use this simple lighting like this is typically the kind of thing that I observe. So we are getting closer, but it's not that yet. You see that I don't have at all this smooth motion there that you've seen in the visual, in the video. So, and the way I can achieve this smooth visual is by using the strobe effect. So the principle is, so here I represented the oscillation of the speaker as a function of time. So when you are in the upper position, you have this pancake shape. When you are in the middle, you have a more spherical shape. Okay, so when you go back to this position, you go back to this pancake shape, and so on and so on. And here, what you can do is that you can, with a strobe, decide to shine. If you synchronize the strobe frequency with the frequency of the speaker, you can decide to shine only some areas that only some moments of this droplet vibration process. So at the end, I can decide to display only this moment, or I can also slightly decrease the frequency, which means increase the time between two strobe bursts. And what you're going to see if you do that is that you're going to light the system when it's a little bit more deformed at every step, and at the end you can have the illusion of a smooth motion. That is not happening actually physically. Physically, the droplet is vibrating at a much faster speed, but here you can really create that illusion of a very smooth motion. And this is what you can see. Oh, sorry. This is what you can see in this part of the video. So you really see that. So don't look at this one. You really see here that there is like this very smooth motion. Okay, so now in the case where I have this oscillation in the horizontal direction, when I have this self-emergence of these shapes, I told you that here there is this parametric excitation phenomenon. And if you want to freeze your pattern, that means that you have to light your system at a frequency that is twice smaller than the excitation frequency. And so at the end, this is very nice because of this pattern is like following this rule. That means that in this experiment, you can just freeze these beautiful modes of vibration. So here I'm like changing the frequency, and like I can freeze this mode 3 shape. This is also from the video that you just seen. Okay, okay. But so at the end, I am measuring because I need to synchronize the frequency of the strobe light with the frequency that excites my speaker. I measure the frequency of that the synthesizer is sending to the speaker with my microcontroller. And at the end, knowing this information, I can control my strobe light. Okay, so now if we look at the video, when we do that, actually it's not there yet either. And you see this kind of thing. If I just look at this with an iPhone, you would see that. Okay. So, and the reason why, it's because you also have to do something with the camera. So if the frame rate of the camera is not the same than the frequency of the strobe, at the end there is some moment when the light is going to turn off in the middle of the sensor exposure, and this is going to happen very randomly. And this is basically what you've just seen in these two videos. And on an iPhone or on these cameras, it doesn't look exactly the same because the sensor doesn't work the same way, but this is exactly the same effect. So you also have to synchronize the camera. So you have to send an electrical impulse that is also triggered by these two, by the light and the synthesizer. You have to send a trigger that basically tells the camera every time the camera receives a trigger to take a frame. So here, the frame rate of the camera during all the performance is constantly changing. So you wouldn't be able to do that with a consumer kind of cameras. And at the end, when you do that, you can see like this very smooth motion. Here I'm starting with a frozen state, and then I play a little bit with the frequency. I can change the frequency even slower. I can really control finely the speed at which you see this pattern moving around. Okay, so now I want to talk a little bit about another experiment that I'm developing. So it's not part of the performance yet. It's before that, before that there is another thing that I developed also for this experiment, which is a 5-axis motorized camera stage in order to be able to do traveling motion. You've seen that also in the video. Sometimes the camera is moving. And so I designed it completely from scratch. It's not something that you can buy somewhere. It's basically, so I did basically some machining, designing. There is a microcontroller and a code that is inspired from a 3D printer system, but it's pretty different. At the end, I really had to rewrite a code and also to think about the interaction. So it's pretty easy in Cartesian coordinate if you just control x, y, and z. But what is very interesting here is to be able also to do spherical coordinates, so to move around objects and to do curves. And this is something that I also developed and still in the process of being developed. So this is so now I'm going to show you. I'm going back to this picture that I've shown you before. It was not very clear at the beginning, and now I just want to tell you a bit what every part is after showing you this sketch. So here you have the projection screen, the computer that drives receives the camera stream. Here this is a 5-axis stage and the camera. It looks like this. Here there is a synthesizer, and here there is like the microcontrollers. So this microcontroller is for the gamepad. This is the light microcontrollers, and this is a microcontroller for the 5-axis stage with a system that comes from a 3D printer to wire everything. And here you have the sound system that was used, the sound generation system that was used by the musician I was working with that day. And here he's using objects with contact mic. Okay, so now I want to tell you about another experiment that I'm currently developing. So this is not part of the performance, but it will at some point. It's based on levitation. So basically, if you put 2 arrays of ultrasonic transducer like this, and you emit ultrasound, you can create an interference pattern. And so basically, a sound wave is a pressure wave. So locally, you create some high pressure zone and low pressure zone. And these interferences are higher pressure difference, are zone of higher pressure difference. So here is what you have in yellow correspond to high pressure, and here it's like low pressure. And basically you can trap objects in that because those pressure are actually enough strong to hold the objects. So here is what the setup look like. So you have like 36 transducers on each side. And here is a video of what you can see. Just I made an iPhone. And what I'm interested to explore here is that this effect that we call persistence of vision, because the object is oscillating, it gives this impression of three-dimensional forms. And so I'm still working on that. This is a video that I did with an industrial camera. Here what you see is me coming with a tweezer and a piece of paper. I'm going to just put the piece of paper in the trap. All right, so this is a kind of visual that you can create. So of course here I want to be able to control parameters and like develop a little bit the playability with these systems. And now I want to give you some perspective on this work. So first of all, the vision, a vision in this project is really to develop a sort of immersive and interactive macroscope, a system that can look at objects and bring them into immersive narrative in which I use the space basically. So a microscope is making very tiny objects visible with your eyes. Here it's like making small objects, not microscopic, small objects, making them huge basically, and being able to put them in narratives. So one of the directions that I want to take is to develop projection mapping for that, being able to project on curved surfaces, being able to project on several screens, this kind of thing. Another thing also that I'm very interested in is to use live image detection. Those cameras are particularly good for that. You can write C code to control them and like embed some live detection codes in it. And so the idea here would be to be able to isolate some of the objects that you see in the image. For example, isolate the droplet, project the droplet somewhere, and project the background somewhere else, for example. And somewhat a vision that is behind this project is like to mix a physics lab with a live performance kind of setup. So I showed you one of the side. I showed you how an experimental physics approach can help somewhat to do performance art. But I'm also exploring the other side around. Like, can the playability that comes from the performance world also help to explore pure scientific aspects? And another thing that I want to mention is the fact that after every performance that I did, at the end there is always people who are very curious about the physics, and they really want to understand more about what they are seeing. And so generally, I become a teacher in these phases. I am really using, in these moments, my artwork as a way to engage people with physics. So, and this is also something that I also would like to explore in the future. And I want to finish this talk by mentioning also all the support. I wouldn't be able to do this project without them. So first of all, the Council for the Art at MIT, who gave me my first grant a year ago when I started this project. The University of Chicago that is hosting my residency. iConcept Labs at Mana Contemporary, which is my art residency. And also my two sponsors, Tor Labs and Pixelinks. Tor Labs make optomechanical pieces. So all the structural parts that I'm using in my experiments come from this company. And the cameras are from Pixelink, those very nice industrial cameras. I also want to thank and mention the people that are involved in this project, either as collaborator or support. So first, Heinrich Jäger, who is hosting my residency. So I have access to all his lab and all his resources to work on this art project. Severinatis, also at University of Chicago. She's a physicist, and she helped me develop the visual. We rehearse together and we perform together. And also the musician, Sam Scranton, Ryan Packard, and Andrew Bregman. And now I would like to thank you for your attention, and I can take questions.
Very nice. So now it's time for questions from audience.
So, what are the tiny bubbles that some of those? Because not everything had a bubble.
Mm-hmm.
What are those?
So they are particles. So yeah, I didn't have the time to really talk about all the physics that you see in this video. But okay, let me go back to the video.
Is it like cavitation?
No, it's not. So I don't know exactly which one you are referring to.
You're talking about the little like vapor bubbles that form inside the bubbles,
Yes.
right?
Are you
Those bubbles, yeah.
here?
Like the top one.
The top one.
Oh, this one. Wait, this one.
No, the one on the top.
Yeah, I mean, I think both of them have it.
So here there is a bubble, yeah. It's just a bubble of air.
Oh, air bubbles?
Air bubbles, yeah.
Okay.
And then something that you could, so here you see also little like spherical shapes, and they are not bubbles, they are particles. So and this is the same kind of particle that you see at the end, here. So here we are throwing particles in the system. The particles, because of capillarity, stick to the droplet and start to create a sort of membrane. And this also changes the mode of excitation and the kind of shapes that you see. And also you see that those particles are like moving around. There is some like flow that is going on at the same time.
Any other questions?
Yeah, so you were talking about how you're trying to study patterns in nature,
Mm-hmm.
right, and not man-made stuff. Like those frequencies that you're using on the water drops, like are those frequencies you would see in nature, or because you had to use a synthesizer
Yeah.
to create those vibrations?
So here at the end, the idea is to create the physical condition. But like the reason why I say it's a natural process somewhat, it's because I'm not creating the contours. The contours are self-emergent. This is what I mean by self-emerging shape. But yes, I'm controlling the physical condition.
And you would see all those frequencies in nature?
Yeah, I mean I don't know if you can see exactly the same kind of very specific patterns, but you can definitely see, like for example, in a lotus leaves, when you have like droplets that are falling on the lotus leaves, can have some oscillation, and those droplets can oscillate. There is also like this kind of parametric excitation, is something that is present in another instability that is basically the image that you see on my first slide. This one. This is called the Faraday instability, and this is something that you observed when crocodiles are like singing in their mating process. So they are singing at very low frequency, and you see this kind of thing at the surface of the water. And this is analogous. It's also a parametric excitation thing.
So why were you doing single droplets of water then?
Just aesthetic choices. You can do also nice thing with that. It's also something that I've been seen a lot around. Like if you, I mean, not in the artistic context, but there is all these people doing cymatics, who are like visualizing music with water, and this is the kind of pattern that they see. The droplets is something that has never been used in art, and I was very interested in that kind of aesthetic. The thing is that also this is a pattern, so it's a repetitive structure. What I'm interested in is like to create some sort of focus, a bit like if you would look at dancer, there is like really a topic. The droplet is a topic. While here it's like more like a pattern that is all around. You don't really want to focus in one specific point, so it's a bit less narrative. It's more like lighting almost.
The other one is you mentioned about the strobe effect, be able to isolate parts of the motion, but in a part you do like you add like a dye
Mm-hmm.
to one of them.
Mm-hmm.
Is that to enhance the way that light interacts with that droplet, or what? Or
No.
Is that different, something different?
No. So this moment is just because it's a nice effect to see like the mixing between these. So you refer to this moment, exactly right. So there is another one. So it's just the diffusion process when you are throwing this liquid that we are injecting here is actually alcohol. So it creates some additional flows, and this is why you have this impression of like some kind of almost a burning kind of patterns. So here it's purely for aesthetic reason. And actually, when you throw either a dye or this alcohol liquid, you change the volume of the bubble, and you also change the way it's going to respond. And you see that here, after doing that, you have some modes that can appear that you are not seeing before.
So in this particular case, that they're all moving differently is because they're different sizes.
There are different sizes, yeah, very good point. And on this one, it's a different composition. Now this one is like part water and part alcohol.
Okay.
Yeah.
Any other questions? I have a couple of questions. So you show like this paper that discussed how these frequencies, like lateral and horizontal frequencies, dictate the emergent shape. So have you done any like theoretical study on the particular shapes that you are creating, or is it the same patterns that you are creating as that paper?
So it's very similar actually. So one regime that is different is the one where you see the particles here.
Okay, yes.
So here you change completely everything. My intuition would be that you can probably write a different surface tension term here that can give like the new behaviors. But no, I haven't studied that quantitatively. And the simple experiment where you just put a droplet on the vibrated plate give like the same basically results that and so they haven't studied here the size of the droplets, but for a given size, if I take exactly the same size, I will basically have exactly the same kind of behaviors.
Another question would be, there are like good software right now where you can model this fluidic behavior. For example, have you tried using like the particular liquid composition and come up with a droplet and like simulate this lateral and horizontal motion and try to see if that model basically behaves the same way?
No, I haven't, and that would be pretty interesting. I haven't played with that. I think it could be also interesting in the art context to do that, because a lot of graphic motors use at the end some physics input, and so being able to like develop the simulation aspects in conjunction with this artistic thing could be an interesting thing. But I haven't explored that yet. Yeah.
Other question? Another question. So one of the first example you showed with these little motorized balls, right, emerge into like a self-sustaining oscillatory state. It kind of reminds me of like swarm robotics.
Exactly. Yeah.
So is there like ongoing research on how these oscillatory behavior could help driving robotic systems?
Yeah. So actually, this work was motivated by swarm robotics. The big idea in this work is that by using self-emergence, the fact that shape can self-emerge, and behavior as well, like this collective behavior, you can somewhat simplify swarm robotic system. Instead of having like a very complex control system, for example here, if you can just switch the response time, you can switch the system from an exploratory kind of state where it's like completely random toward a regime where you have like collective behavior. So it's really like, it was really the idea actually. The motivation was swarm robotics and how to build swarm robotic systems that are more simple thanks to physics, thanks to the physics of self-emergence.
Actually, one more.
Go ahead.
So you showed your lab setup. You have multiple different components that you kind of choreograph together. How tolerant are those? Like, because especially the Arduinos that don't really have like the exact same clock cycles. Like, how tolerant is the system for like one process going slightly faster, the other one going slightly slower, and that stuff? Like, or the system are you like constantly monitoring for that variations?
Yeah, that's a good question. So I'm actually only using one clock in that system for the light, and on the image that I showed, it's an Arduino, but now I'm using actually a Teensy because the clock was bad on the Arduino. On this thing, yeah, this thing. So this now is, which is a light microcontroller, it's replaced by a Teensy. But I don't have these kind of problems that you are mentioning, because the clock only is only managed with one controller. I don't need clock for the 5-axis stage. This is passive, and the only thing that I'm doing with this is measuring the frequencies that come from the synthesizer, from the audio signal. So it's just a measurement, measuring that clock, and then every time and knowing this clock, I send at the same frequency or a close frequency, I send a TTL, a 5-volt electrical TTL, to the camera, and the camera just reacts to that by taking a frame. So there is no clock outside of this guy. So I don't have this kind of clock issue. But it's true that it's an important aspect, and I had to think about a way where I don't have this kind of problems for the system.
So computer science students, AI students, any questions? Okay, oh, never mind. I think we ran out of time also, but let's thank again our speaker.
Thank you.
Very interesting talk. That was great.
Thank you.